Hello, everyone. Welcome to Calculus Lecture 2. And today we'll start with a review of trigonometric functions, and then we'll continue talking about limits. So let's get started. The first thing we want to remember is the way that standard trigonometric functions are defined. So one good way to remember this is SOHCAHTOA. And this means if you have an angle inside a right triangle, so this is a right angle and this angle is theta, then the first is that sine is the opposite over the hypotenuse. So sine theta is going to be, let's call this side A, B, and C. Then the opposite side to theta is B, and the hypotenuse is C. So sine theta is B over C. Then cosine theta, this is the second part of the mnemonic, is the adjacent side over the hypotenuse. So that's going to be A over C. And then finally, the tangent to theta is going to be the opposite over the adjacent. So that's going to be B over A. And you'll notice that the tangent is also equal to the sine over the cosine. So that's also always true. Another way you can think about these is using a unit circle. So if I have a circle of radius 1 centered at the origin. See, all right, and then we have like any angle, and this works even if theta is greater than 90 degrees. So say this angle here is theta. Then if you drop the perpendicular, this distance here, whatever that value on the x-axis is going to be cosine of theta. Note that in this case it's negative because it's to the left of 0. And this value here on the y-axis is the sine of theta. Cosine and sine are always between -1 and 1. The tangent is not bounded. You'll also know that there are a few more functions that aren't as common, but the cosecant, or also sometimes notated CSC, is 1 over the sine. The secant is 1 over cosine. And finally, the cotangent is 1 over the tangent. And finally, we have inverse functions to all of these. So what these are, and I'll only go with the main three. So we have arc sine or sine inverse. And what an inverse function does is you have the value of like sine theta, and you want to get back theta. So the inverse undoes the operation. Now you want to be careful here because sine, cosine, and tangent, these are not injective functions. So even if you have a value for sine theta, there isn't only one value of theta that could have had that same sign. So it's going to spit out a value in a certain range. And it's the unique value in that range, but it's not the only value of theta that'll give that value of sine. So the range of arc sine is going to be between -π/2 and π/2. This is just by convention. Well, you could have chosen something else, but the arc sine, if you put this into a calculator, will always give you the value between -π/2 and π/2. For arc cosine, so this is the inverse function of cosine. Now the range is actually different. this is going to be between 0 and pi. And finally, for arctan, or the inverse of the tangent function, the range is going to be between negative pi over 2 and pi over 2, but this time we don't actually include the endpoints. And the reason for this is because tangent of negative pi over 2 or pi over 2 or any multiple of pi over 2 is not defined, because it's sine over cosine, but cosine of pi over 2 is 0. The other thing to know here is what these graphs look like. So let me just draw out the graphs for sine and cosine and maybe tangent. So for sine and cosine, the maximum value is always going to be 1, and the minimum value is going to be -1. And the important points are on the x-axis are the multiples of pi over 2. So let's say that's pi over 2, that's pi, that's 3 pi over 2. And on this side, we have negative pi over 2, negative pi, and negative 3 pi over 2. All right, so sine of 0 is 0. All right, sine takes the maximum value at pi over 2 of 1. Then sine of pi is again 0. All right, and then it takes a minimum of -1 at 3 pi over 2. And the same pattern continues on the left. So it also takes this minimum at negative pi over 2. Then at negative pi, it's 0. And at negative 3 pi over 2, it's going to be maximal at 1. So basically this graph, it's a wave that looks like this. And cosine is just like a shifted version of sine. So now we actually start from a maximum. Cosine is 0 is equal to 1. So we start here. And then cosine of pi over 2 and negative pi over 2 is 0. So let's just label this. So the purple is cosine x. And again, we're going to have a minimum here. And it takes on exactly the same form. And now we're going to have a wave that looks like this. The graph of tangent is a little bit different. It'll actually have some asymptotes because when cosine is 0, the tangent is undefined and it goes off to infinity. And those are all the multiples of pi over 2. Now let's talk about some trig identities that are good to know. So I'm going to go over 4 categories of identities that are really important to know. So first we have the addition and subtraction identities. So I'm going to just write down these formulas for sine, cosine, tangent of a plus b. So sine of a plus b is going to be sine a cosine b plus cosine a sine b. Cosine is slightly different. We're going to have cosine a plus b equals cosine a cosine b minus sine a sine b. So now we have the same thing in both the terms. Tangent actually has a fraction here. And tangent is, remember, sine over cosine, but we actually have a different formula in terms of the tangents. And this is going to be equal to tan A plus tan B over 1 minus the product. There are also similar formulas for the differences. So for sine A minus B, for cosine A minus B, and tan A minus B. So let's write these down. So these are just going to flip a few signs because cosine and sine will differ by a sign. So sine of negative x is negative sine of x. Sine is an odd function. And cosine of x is cosine of minus x because cosine is an even function. And so these just have a few sign flips based on that. So we're going to have sine A cosine B minus cosine A sine B. All right, here we're going to have cosine A cosine B plus sine A sine B. And here we're going to have tangent A minus tangent B over 1 plus the product. Now, from these, we also get the double angle identities, which you can just get from these, but this is when you have A equal to B, and so you can get like a formula for sine 2A or cosine 2A or tangent 2A. Let's write down these as well. So sine 2 theta, just from the formula before, this is going to be 2 sine theta cosine theta. Cosine 2 theta is going to be cosine squared theta. Remember, that means cosine theta times cosine theta minus sine squared theta. And there are a few more ways to formulate this that you can work out. So this also equals 2 cosine squared theta minus 1. And it also equals 1 minus 2 sine squared theta. So you can use whichever of these is convenient. And finally, for tan 2 theta, we have the formula, this is equal to 2 tan theta over 1 minus tan squared theta. These formulas that I've just gone over, especially for sine and cosine, are really important to know. Now, let's talk a bit about the product identities and half-angle identities. The product ones are also pretty important to know. I have never personally had to remember the half-angle identities, but you might have to for your class. So in that case, I'll give them to you. So let's start with the product identities. So here we're going to have these formulas for sine A cosine B. That equals 1/2 times sine A plus B plus sine A minus B. Cosine A sine B is going to be 1/2 sine A plus B minus sine A minus B. That's like this. All right, now we have cosine A cosine B. That's 1/2 cosine A plus B plus cosine A minus B. And finally, sine A sine B is 1/2 times cosine A minus B minus cosine A plus B. So you don't necessarily need to just blindly memorize these formulas. You can actually get them from the sum and difference formulas. So for example, if we go back here and we want to look at cosine A, cosine B, and we want to get a formula for that. So we have it here and we have it here. And so if we add this equation to this equation, then the other term will actually cancel because there's a negative in one term and a positive in the other. And so we'll get that 2 cosine A cosine B equals cosine A plus B plus cosine A minus B. And then we can just divide by 2 to get that cosine A cosine B is 1/2 times cosine A plus B plus cosine A minus B. And you can do something similar for all of them. So that is another potential way to remember these formulas. And in a minute, I'll go over another way we can also memorize the addition and subtraction formulas, which might be easier for you. But first, let me just quickly go over the half angle identities. So now we have sine theta over 2. All right, this is going to be, we have a plus or minus here because there's a square root, and we don't actually know which one it is. But it's going to be this plus or minus the square root of 1 minus cosine theta over 2. For cosine theta over 2, it's going to be plus or minus 1 plus cosine theta over 2, the square root of 1 plus cosine theta over 2. And finally, for tan theta over 2, that's going to be plus or minus the square root of 1 minus cosine theta over 1 plus cosine theta. And you can see this by dividing the other two. All right, so let's quickly talk about a way to derive the formulas for the addition and subtraction, and also the double angle formulas follow from those. So I'm going to define something called a complex exponent. You don't have to remember this if you don't want to, but I just find it an easier way to remember the sum and difference formulas. So basically, you can define a complex exponent, e to the I theta, to be cosine theta plus I sine theta. This is just a definition. But the really cool thing with this is that the laws of exponents work exactly as you would expect them to. So for example, e to the a theta plus times e to the b theta, that's equal to e to the a plus b times theta. And you can expand this on both sides. So over here, we're going to have cosine a plus I sine a times cosine b plus I sine b. All right, and over here, this is going to be equal to cosine a plus b plus I sine a plus b. Now, if you expand out this, what you'll get is that cosine a cosine b minus sine a sine b, we're going to get an I squared there that turns into a minus 1, plus I times cosine a sine b plus sine a cosine b. Right, that's going to be equal to this over here. So that's cosine a plus b plus I sine a plus b. And then you can set these equal, and you can get that cosine a plus b is equal to that, and sine a plus b is equal to that. And you can always add negative signs where you need to. So that's just another helpful way. If that didn't make sense, don't worry about it. You don't need to know this, but it might be easier for you. All right, so now let's go back to talking about limits. So just to recall from last time, a function has a limit at some value x if its left hand and right hand limits are the same. And if there's no limit, then we can say that the limit does not exist, and we'll usually just write dne. So I'm going to give two examples right now, and then pause for a minute so that you can try to answer this on your own, and then we'll go over the answer. So the first one, I have a graph that looks like this. All right, and then there's an open circle here and here. So the graph is not defined at 2, but away from 2, it looks something like that. So the question is, what are the left and right-hand side limits as x approaches 2? And does the limit exist? I'll pause for just a moment here and then go over the answer. All right, so we can see here that as we approach 2 from the right side, so now we're following this curve. So the function value is approaching 4. So we're going to say that this limit is 4. All right. Meanwhile, if we approach from the left side, then we're following this curve. And so we're approaching this point at 3. So the limit from the left is 3. And because these are not the same, the total limit does not exist. All right. Let's do one more example. Here's a linear graph, but it's not going to be defined at one point. So let's again just draw our coordinates. All right, and just so that it's clear here, this point is 3,5. That is not on the graph. And again, the question is, what's the left-hand limit, what's the right-hand limit, and what's the total limit if it exists? I'll pause for a moment. Feel free to pause the video. All right, so if we approach from the right, well, we're heading towards this point at 5. But the same is true if we're approaching from the left. We're still heading towards the same point. So in fact, both the limits are 5. And because they are the same, the limit as x goes to 3 of f of x does exist, and it is 5. All right. Let's do 2 more with slightly different looking graphs. And then we'll go back to doing some limits with equations. So that'll be a little bit trickier. So let's do 2 more graphs first. Sorry. So this is 1, 2, 3, and 4. All right, and then 1, 2, 3, and 4. So we're going to have a graph that looks like this. But then we're going to have 1 point excluded. And we're going to have a circle here, and this point is 2, 3. So now the question is, what's the limit as x approaches 2 of this function? All right, so here we can see that if we follow the graph around 2, then we're heading towards this point, 2, 3. And so the limit is going to be 3. All right, and one more that's slightly trickier, very similar. Let's just draw it on the same grid. So now we're going to have this and an open circle. So it starts out the same way, but then it's going to be filled in over here. And then we're going to have another thing. So now we're going to need to look at the one-sided limits. So the question is, what's the limit as x goes to 2 from the right? What's the limit as x goes to 2 from the left? And finally, what's the total limit if it exists? All right, again, I'll pause for a moment, but feel free to pause the video. All right, so here, if we approach from the right, then we're going to follow this line, and this point is 2, 1. So the limit from the right is 1. Meanwhile, the limit from the left, now we're going to follow that line, and now we're heading towards this point, which is 2, 3. So then the limit from the left is 3. And because they're not the same, the limit as x goes to 2 of f of x does not exist. All right, now let's try some functions. So here's one. Remember that we spoke last time about continuous functions. So if a function is continuous, then the limit does exist and is equal to the value of the function. And we also know that all polynomials are continuous. So based on that, let's try this example. All right, and we're going to do one more example after this. I'll write this one down too, and then pause for a minute. All right, so for the first one, this is a continuous function, which means all we need to do is plug 2 into it. So we're going to have 8 minus 3 times 2 plus 12 times 2 squared. All right, so that's 8 minus 6 plus 48, if I'm doing this right. And I believe the answer is going to be 50. All right, the second one's slightly trickier. Let's just pause for a moment again. All right, so now this function isn't quite going to be continuous because when the denominator is 0, then the function will not be defined. So to figure this out, we need to factor the numerator and denominator. And then we can cancel because the limit doesn't care about the value of the function at a point, but only around the point. So x squared minus 25 is the difference of squares. So the numerator is going to be equal to x plus 5 times x minus 5. And the denominator is going to be equal to, well, we need two numbers who multiply to 15 and add to 2. So it seems like that's going to be 5 and negative 3. So that's going to give us x minus 5 times x plus 3. So it seems here that we can cancel the x minus 5. And then we're left with the limit as x goes to minus 5 of x plus 5 over x plus 3. And now we don't have to worry about the denominator being 0 around minus 5. So we can just plug that in. So that's going to be minus 5 plus 5 over minus 5 plus 3 equals 0 over negative 2. So that's just 0. Okay, so let's do one more example. This time it'll be slightly simpler, but it'll be a piecewise defined function. So we're going to define this function f of x to equal 7 minus 4x if x is less than 1, and x squared plus 2 if x is greater than or equal to 1. All right, and the question is, what's the limit, if it exists, of as x goes to -6 of f of x? And then what's the limit, again, if it exists, as x goes to 1 of f of x? All right, so when x is going to -6, well, now we're well into this range. -6 is less than -1. So we don't actually have to worry about multiple sides because it is just defined to be this polynomial equation around -6. So we just plug that straight in. So that's going to be 7 minus 4 times -6. So that's 7 plus 24, which is 31. Now, as x goes to 1, we have to be a little more careful because now it's defined as two different things near 1. So we're going to need to work out both and see if they're the same. So here from the left, the limit is going to be 7 minus 4 times 1, which is 3. And from the right, it's going to be x squared plus 2 when x is 1. And that's also 3 because 1 plus 2 is 3. And in fact, because both of these are the same, the limit does exist. And we're going to get 3 as our final answer. So there's one more topic I want to discuss, which is an infinite limit of rational functions. So let's do one example here. So the point is to evaluate the limit as x goes to infinity of this function, 4x squared plus x plus 6 over 3x squared plus 1. Again, I'll pause for a moment so that you can think about it, and then we'll discuss how we would work out something like this. All right, so the main thing to know about rational functions is that the leading term always dominates. So when you're taking a limit, you can pretend the rest of the terms don't even exist because the leading term gets so big that the other terms don't matter. So this is the limit as x goes to infinity of 4x squared over 3x squared. And then the x squared cancels, and that's just going to be 4 over 3. So it's 4/3. Now, in general, if you have a polynomial function, now in this case, we had an x squared on the top and an x squared on the bottom, so they canceled. If the exponent on the top was bigger, so the numerator has higher degree, so say this was an x cubed instead of an x squared, well, in that case, we would have x cubed over here, and we wouldn't quite be able to cancel. We would get 4x over 3. But now because x is going to infinity, the whole thing would go to infinity. And so in all cases, if the numerator has a higher degree, then it'll go to infinity. But it could also be the other way around, that the denominator has higher degree. So in that case, say we had an x cubed on the bottom and not on top. So we'd be looking at the limit as x goes to infinity of 4x squared plus x plus 6 over 3x cubed plus 1. Well, again, we're only looking at the leading coefficients, but then we're going to get the limit as x goes to infinity of 4x squared over 3x cubed. And after canceling, that's going to be the limit, again, as x goes to infinity, of 4 over 3x. But now we have an x in the denominator that's going to infinity, which means we're dividing by a really big number. And so the whole thing's going to 0. And that's also always true. So if the denominator has a higher degree, then the entire limit goes to 0. So let's do a few examples for practice. All right, I'll just pause for a moment again. All right, so in the first example, the numerator has degree 2 and the denominator has degree 1. So as we just discussed, this will go to infinity. In the second example, it's flipped. The denominator has degree 2 and the numerator has degree 1. So now this will go to 0. The denominator gets large faster than the numerator does. And then the last one, we have the same exponent of 5 in the numerator and denominator. So here we're going to get, again, we can ignore all terms except the leading terms. So this is the limit as x goes to infinity of 10x to the 5 over 3x to the 5. And we can cancel these, and we get 10/3. All right, let's do 3 more practice problems. Okay, so the first one, we're just going to stare at the leading coefficients. So this is going to be 3x cubed over negative 2x cubed. And the x cubes cancel. And so we end up with negative 3 over 2. The next one's slightly trickier because we have a negative infinity. So again, we only need to care about the leading terms. So this is going to be the limit as x goes to negative infinity of x cubed over x squared. The x squared cancels, so that's the limit as x goes to negative infinity of x. And of course, x is going to negative infinity, so the answer is going to be negative infinity. All right, and finally for the last one, we're going to factor the numerator and cancel. So we're going to get the limit as x goes to a of x plus a times x minus a, just a difference of squares, over x minus a. And now we cancel, so this cancels with that, and this is the limit as x goes to a of x plus a. And what we get here is just, we substitute that in, so we get a plus a, which is 2a. All right, and we'll stop there. Next time we'll start talking about what a derivative is. So we'll really be getting into the calculus part of this class. All right, thanks for watching.